Hello, we're going to deal with entanglement and the many worlds interpretation of quantum mechanics and the mysticism that this leads to. So let's jump right into it. Here we go. Okay, we have a whole cast of characters here. Up here we have Albert Einstein, who was instrumental in uh, kicking off activities into quantum mechanics in the world of the microcosm. Uh, right next to him, though, we have someone you're not familiar with, Hugh Everett, who is the one who came up with his many worlds interpretation of quantum mechanics, where, if you will, there's multiple timelines that evolve every instant. There's another timeline being created, branching off as different choices are made. And that's going to be the focus of our discussion today, and how this leads to entanglement, how different things get caught up and linked to one another. Over here, we have Niels Bohr, and Niels Bohr is here, and Werner Heisenberg is here. And they were the key people in the early days of quantum mechanics in the 1920s, and they came up with what many now view as an ad hoc interpretation of how quantum mechanics worked, whereas today many people would agree that what Hugh Everett came up with his multiple timelines, many worlds interpretation, is what's really going on. Down here, we have Wolfgang Pauli and Carl Jung, who worked for decades together on what became synchronicity, which got superseded by this many worlds interpretation. And over here, we have Louis de Broglie and David Bohm, two physicists who came up with a so-called pilot wave interpretation for quantum mechanics that we believe is now the correct one. So a lot of characters here, a lot of things going on. We're going to start with simply the baseline case, which is what people believe they see the world around them with so-called classical view of Isaac Newton. Then we'll jump into the quantum view of things and close out with just touching on how general relativity enters into all of this. So up here we have Isaac Newton, and Newton felt it was quite straightforward. There's three dimensions for space. There's one dimension for time. There's no coupling between space and time. They are what they are. And that's worked for hundreds of years. And it was only in the late 1890s, early 1900s, that breakdown started to appear, which we could summarize here as if you go faster and faster, time slows down for you, which is showing that there's something funny going on here, because you're moving through these three spatial dimensions more quickly, and yet time is slowing down. So there's a coupling between space and time. And another one is, as gravity increases, time slows down. So again, space, the three spatial dimensions involve gravity, and time here is, again, coupled to them through gravity. So there's a breakdown that's occurring here in this, and there's other problems as well that we'll get into. So let's jump in here with Newton. And we also have a picture here of Max Planck. Newton believed that light was made up of tiny particles called corpuscles, because light travels in a straight line. It doesn't appear to curve, and it doesn't appear to exert pressure. In fact, it does exert pressure, just that Newton couldn't measure it. But in the decades after that, Jung showed that if light went through two closely spaced slits, say in a screen of some sort, there was an interference pattern that arose. So light had to be a wave. You can't get a interference pattern by just having particles go through two different slits. You'll just end up with two lines. If it's a wave, you'll end up with an interference pattern here. Then we jump to Max Planck around the 1900 timeframe, who explained black body radiation, that is, radiation coming from a body that's totally black. So this is heat, but it encompasses electromagnetic radiation as well, all radiation. And the only way he could explain what's going on was that he said that light wasn't a wave, but rather was made up of discrete particles that had discrete quanta of energy. Today, we would call these photons. And in 1905, Albert Einstein explained this, a photoelectric effect, shining light onto a material would generate electron flow. And this could only occur if the light was made up of discrete particles, not as a wave. So here we start to see the breakdown between classical quantum mechanics. There's the so-called double slit experiment. In the classical realm, you can look at ping pong balls that are shot through a slit in a screen. The ping pong balls would form a line on the other side of the screen, quite straightforward. And then we look at a water tank, and a water tank would have a screen in it with two slits. The waves of water would move toward the screen, and on the other side, the waves that would come through would interfere constructively and destructively to create an interference pattern. Now, when we go to the quantum realm, where we now shoot not balls, but electrons, we see that if we have one slit, that there's just a line there, but if we shoot at two slits closely spaced, what happens is the electrons show an interference pattern. And we could test this by going slower and slower, one electron at a time. If we looked at the two slits there and the electrons going through, then we wouldn't see an interference pattern. So apparently the observer can influence what's going on here. And so it goes. So having said that, this led to Niels Bohr here and Werner Heisenberg here, meeting in Copenhagen over a number of times, the 1925-1927 period. And they came up with what would be called the interpretation of quantum mechanics. Their interpretation was that when we had these one slit versus two slits, and with the observer, that the quote unquote wave function that you have in quantum mechanics, which describes everything, that it collapsed, okay, that there was no longer any uncertainty. Whereas prior to looking at it, what Max Born had argued for was that the square of the wave function, the magnitude squared, because it's a complex function, we need to take the real and imaginary parts and square them, add them together to get the total squared magnitude of the wave function. That defines a probability of where the wave function entity would be, and so it goes. So having said that, this would collapse to not to a smearing of any sort, but a particular point in space, for example. The thing that comes about through this, though, is that quantum mechanics is intrinsically probabilistic or indeterministic. You have to use this rule that Born came up with for scoring the magnitude of the wave function. And there's a principle of complementarity, which states that if I measure precisely, for example, the position of an object, then I can't measure the velocity of the object or the momentum of the object at the same time, that there's a basic intrinsic uncertainty here. And so the act of observing or measuring is irreversible. That is, once we actually carry out this measurement, that whatever it is that got measured doesn't change, but the other things can change. And this leads to what many would view as a very ad hoc interpretation, and the observations determine the theory rather than the theory determining what the observations are, which is not acceptable to many physicists. Building on this, we had two people, Wolfgang Pauli, a physicist, and Carl Jung, who's a polymath, built on this, and they carried out a correspondence over decades, 1930 to 1957, and they tried to resolve some of these contradictions, which led to the notion of synchronicity. Synchronicity for Pauli arose because, as a theoretical physicist, he had many experimental physicists that wanted to show him experiments. So he would visit their labs. As he walked in the door, literally the experiment would collapse. There would be no experiment to be shown to Pauli. No one could understand this. And this was called the Pauli effect. And they called this an acausal notion of what was going on. And Jung worked on this to develop this non-causal principle, which resulted in acausal connections as well as causal connections to understand what's going on in the world. Really, not a lot of physicists pursued this because there was a second idea that came up that was intriguing to people called the pilot wave theory of quantum mechanics. So Louis de Broglie, who in his 1924 thesis postulated that electrons that were particles actually were also waves, and they had a wavelength. And he suggested that all matter had wave properties. And the end result of this was that this was actually experimentally demonstrated, which nobody believed, of course, when he first did it. And he was awarded the Nobel Prize. But for them to explain this theory of this in this double slit experiment, de Broglie thought there would probably be some sort of pilot wave, some sort of control mechanism that wasn't being detected here. And he argued for this. It was dropped until 1952 when David Bohm, shown here, picked up on it, and he developed a whole theory here of this that he called the implicate and explicate order. He believed that the brain works according to the mathematics of some quantum effects, and he postulated that thought itself is distributed, non-localized, just as quantum entities are. So he developed this theory, which is completely consistent with the quantum mechanics that physicists were using. And it led to a deterministic or mechanistic viewpoint. The problem was that it was hard to understand this because this pilot wave was some sort of radiation that was in some other band than anything was measured in. And so he called it a hidden variable theory or an ontological theory as opposed to anything else. And what we'll see here is that while this met a lot of skepticism and was really negatively received, there was an openness toward reviving this idea, and it continues to this day. And really what happened was Ron Cowan in the 1990s onward was able to achieve a great deal of clear seeing or clairvoyance in deep meditations. I encourage you to go to the Yoga Sutras of Patanjali, particularly the book 3, Sutras 25 to 30, and you'll see what he was doing here. And in particular, Ron saw that the space itself formed discrete compartments, quanta, and collectively they make up a foam that makes up space around us. But these compartments are coded inside with blocks of information that are constantly scanning the world around us. We don't know what the mechanism is for doing the scanning. Whenever there's any change that's detected, the information has algorithms in it that react accordingly. So here's a picture. Ron was able to stop an electron, which is actually 10 closed strings, and energy resonates inside this. So really an electron is more like a jelly bean, if you will. The 10 strings are vibrating, energy goes in here, and it effectively to us looks like a particle, but it isn't. It's actually a torus. There's a hole through the middle, as you can see here, looking down on it. And the blocks of information for the electron are just covering it, okay? So here are these blocks, and they're constantly scanning, and that's what happened in this double slit experiment. When there's two slits, the electron immediately behaves as a wave. When there's one slit, it behaves as a particle. I don't know why, but these are the algorithms that are there. And this leads to the notion that information controls everything. It controls the physics of what we call matter, which is made up of subquarks. These are typically 10 closed strings, and they make up what are called bosons, electrons, and so forth. And that continues on up all through the hierarchy of matter, chemistry, and biology. But we also have dark matter, which is 5 strings, 5 closed strings, And these just don't have any charge on them, unlike those associated with matter. So they end up just being a subatomic, a nuclear chemistry here that controls what is dark matter, which appears to be actually sentient and immortal. And so information is critical to everything here. So the probability and many worlds interpretation go hand in hand here. As we're going to see in a second, there's two facets at the outset in quantum mechanics. Why should we assign probabilities at all to outcomes that are certain to occur, and maybe they aren't certain to occur? And there's the quantitative problem, which is why do we have these probabilities governed by this Born rule? What's going on? So Hugh Everett did his doctoral dissertation under John Wheeler at Princeton, and he tried to answer these questions. Most people would run for the hills. This is really, foundational stuff, very hard to understand. So the end result was that Everett proposed a derivation of the Born rule that we talked about, that there's a branching that occurs in the wave function at every instant. And so we have timelines or worlds, and they keep splitting off from one another, splitting. But we could think of these timelines as, if you will, clustering together. So there's a cluster of timelines around a certain set of events, and there's a cluster of timelines around other events, and so forth. And other people have come in on this as well. This is really a meta mathematics question. It's almost philosophical, because the assertion is that the wave function, which encompasses the entire universe, is something real, and the wave function itself never collapses. So it's always there. You're always dealing with this wave function, but it keeps branching, and creates different worlds here. Hugh Everett proposed this, and Bryce DeWitt, a physicist, popularized it and decided to call it the many worlds interpretation. Everett did great work. I've actually read his doctoral dissertation, and he has a set of assumptions there, but they're perfectly plausible assumptions. The problem is, how do you test these things? They're just assumptions. And Everett wasn't the first person. Erwin Schrödinger, one of the key founders of quantum mechanics in the 20s, went on to assert that the Schrödinger equation seemed to describe several different histories, and they all seem to be happening simultaneously. That is the many worlds interpretation. And so Everett and Schrödinger are linked in this sense. Schrödinger's writings from this period also resemble a modal interpretation by someone else. And Schrödinger described a kind of a Mach. Mach is a philosopher in Austria, a post-Mach neutral monism. Matter and mind are only different aspects or arrangements of the same common elements. And this led to other people working on this. But the reality was that the physicist community was overwhelmingly negative to this, with exceptions, of course. And the end result was that Hugh Everett just decided to drop completely out of academia. He never returned, and he was totally disillusioned by the flack that he took from doing this. Many other people, like David Deutsch today, call this a meta theory, or as opposed to a many worlds theory. It's just an interpretation of the solution to the wave equation. And so the crux of what Everett did here is that he had the concept of a relative state. So we have two or more subsystems, say an observer and a system, say that the system contains an electron gun, some electrons, and a double slit with a screen behind it. And so they become correlated. The observer is looking at what's going on with the double slit. So they're now entangled. Or there's only one slit in the other subsystem and the observer, and they're entangled. So this results in the different entangled systems can be mathematically written down. They each have a state relative to each other. And if you carry out a measurement and so forth, then you've recorded the state of the measured system. So once they interact, their states have become correlated or entangled, and they're no longer independent. And that's why Everett uses the term correlation as opposed to entangled. Entangled is a more modern thing. But a typical example here is a box that contains a cat, and the box is closed. There's a poison vial in there that is in glass, and it's on a string with a mechanism holding it. And the question is this: if the vial doesn't break, then when you open the box, you'll see the vial and the cat is alive. But on the other hand, if the vial breaks, then the cat dies, and you have a broken vial and a dead cat. And so you have these two different states, and they're entangled with one another. Which one is it when you open the box? And that leads to all kinds of things. So having said that, Everett tried to get away from this notion of Bohr and Heisenberg of having a collapse of the wave function so that the electron in the double slit experiment magically became a wave. And he said that really the wave function is there all the time, and you don't understand what's going on, but there is no collapse. In one realm, it appears as a particle, and another it appears as a wave. But the most likely thing that we see is it appears as a wave when there's two slits, and appears as a particle when there's one slit. So every observation that causes this to change results in a change in state, and we create more and more universes, more and more timelines here along the way. Everett ended up running with this thing, did a lot of interesting calculations, and the end result is that there's, again, for every instant that things can change, everything happens, and that we have all of these simultaneously existing worlds or timelines. And the thing to keep in mind here is this is consistent with what Louis de Broglie and David Bohm came up with. And it appears to be really the true interpretation of what's going on here. It supersedes what Pauli and Jung did with notion of synchronicity. It's a superset of that. But the problem this results in is there's all of these timelines, so they're just uncountable in number. They keep splitting with every instant, and so it goes. The thing that makes all this possible is the linearity of the actual wave equation. The fact that if you double the wave equation, then the output doubles. If you add two wave functions together, the output is the sum of the two wave functions. And so this notion of linearity applies everywhere, and it applies throughout the universe, and it gives you a handle on what's going on. Whereas the Copenhagen interpretation was really a sledgehammer, and you can't really figure out where in the world this thing came from. So there really is no division between classical and quantum realms here in this many world interpretation, and it's a very exciting thing that has led to people carrying out all kinds of experiments today that confirm that this is indeed true. The theory is actually based on reality. It's deterministic, and it's local. The entanglement occurs locally, and then things could move far apart. They could be millions of miles apart, but if they're entangled and I change one thing, then the other thing will change instantaneously, even if it's millions of miles away. And that's what was spooky to physicists, but it's what in fact comes out of the mathematics of quantum mechanics. So you can, sometimes the problem is you don't take your theory seriously enough. This is an example of people not wanting to believe what in the world force, what in the world field is there that would couple these things. And here in this regard, we ended up seeing, the key thing is to get away from this wave function collapse, which was regarded as artificial and ad hoc, and so forth. But having done all this, the physicists walk away from it, and that was their mistake. They should have taken it more seriously. David Deutsch, shown here with Hugh Everett, is still actively, and he's in England, is actively pursuing this, and so it goes. And the notion of entanglement is really a feature that's unique to quantum mechanics. You simply don't find this in classical mechanics, and that's why your intuition for it doesn't really hold. So the coupling between these things, the entanglement that occurs in things, for example, if I measure the position of something, then the momentum or the spin or the polarization, all of these other properties still could be all over the place, and have a distribution of values. But the changes that occur affect the system as a whole, not just one or two particles in it, but the entire system is affected by this entanglement. So having said that, you end up with quite frankly, a mess, a really composite state that describes what's going on. We've got an example where a subatomic particle decays into an entangled pair of other particles. So there's conservation of energy, conservation of momentum. And so the measurement outcomes of one particle are highly correlated with the measurement of the other particle, and so forth. And this ends up, if we measure the spin of the first particle, and for example, we find it spin up, then the other one is also found to be spin down, or vice versa, because these particles end up obeying an exclusion principle due to Pauli, that you could only be in one state. You could either have an up state or a down state, and you could have both of them together, but that was it. And so a great deal of work has been done in the past decades on showing that this entanglement really is a real phenomenon. And that takes us up to the present time. But we haven't said anything about general relativity. So I'm just going to touch on this briefly. What Einstein showed was that gravity results from the curvature of space-time. The more curved it is, the greater the mass, and the more attracted you are to whatever it is. John Wheeler at Princeton argued that space is made up of discrete compartments, and that there's a quantum foam that makes up space all around us. And Alan Guth and Eric Lindy showed that these space compartments could in fact expand when the universe undergoes its bounce at inception, and they will collapse when it goes at the other end of the bounce back to compaction. So the space compartments can expand. So we could have something in a space compartment that could be light years long, and they can contract and expand. But you say, well, this thing is far away, but it's in the same space compartment. And this is something that Ron Cowan observed, was that these space compartments, which obey this Pauli exclusion principle, by the way, They can be light years long, and they can transit back, and the entanglement could indeed be due to this as one mechanism here for describing what's going on. So that's it for today. Have a good, and we'll take it from here.